All right. Hello, everybody. Good afternoon. Let me apologize in advance. I'm recovering from something, and I have a bit of a cough, and my voice isn't great, but I'll do my best. So anyway, I'm Tor Norbye, and I'm here to talk to you about Lint, what it is, and how to write your own checks. This is actually my second time speaking about Lint at KotlinConf. This is the title slide from the first time, the very first KotlinConf in 2017. So check out that old Kotlin logo on the top left. Anyway, a lot has happened since then, so don't worry, the rest of the slides are new. So first, let's talk briefly about what Lint is. And to illustrate that, I'll cover some of its features. So at its heart, it's a static analysis tool. It inspects your code, finds things that are either definitely wrong or maybe suspicious of bad practice or bad usability and so on. And we report those as warnings. Android Lint started as a static analysis tool for Android in 2011. So it's a teenager, actually. But many of the bundled Lint checks weren't Android specific. And some of the companies using Lint for their Android apps thought it was so useful that they wanted it for their server-side code too. So they would work around it by creating fake Android wrappers around their server libraries. So because of that, we generalized Lint a bit, and for the last 8 years or so, it has been a general-purpose static analysis tool with an unfortunate name. When Google adopted Kotlin, it became necessary to migrate from the static analysis tool we were using for Java, error-prone, to something which can support both Kotlin and Java. And Android Lint fits the bill. So these days, Android Lint is used to analyze all Kotlin and Java code inside the Google code base. We're talking about a lot of invocations and a lot of builds every day. Just the Kotlin part yesterday I heard is 30 million lines of code. All right, so I mentioned that Lint reports potential problems in your code. How it reports those problems depends on where Lint is running. So when it's integrated in the build system, it can create report files like JUnit or text output and break the build if it finds a serious error. When it's integrated in the IDE, it produces highlights in the editor, and it runs in the background when you're editing Kotlin files and Java files and XML files and so on. And that's because Lint is multilingual. So it's architected to support finding bugs in a bunch of different file types. Many of these file types are code, but in Android, for example, there are a lot of usages of XML for strings, icons, and declaring requirements in something called manifest files. So Lint can analyze all of this and even binary files like class files and icon files. We actually have Lint checks which make sure that your notification icons follow the expected visual style, being monochrome. So as part of this, Lint also makes it easy to do cross-reference checks. So take a look at message catalogs, for example. On the top here, you can see a typical formatting string mistake. We're passing in a string for a placeholder that is expecting an integer, and that's going to crash at runtime. But in Android, typically messages are separated out into separate files, and they're going to be analyzed separately. And so it's an important task for Lint to be able to handle this and to catch these kinds of consistency mistakes. So Lint obviously comes with a bunch of Lint built-in checks. We're inching up towards 500 at this point. I already mentioned that Lint is integrated in the IDE. And some of these checks can only work if it can look at all the code, such as unused resources. But 90% of the built-in checks are actually running on the fly as you're typing every few seconds. And around half of them are related to Kotlin and Java code. And the percentage is lower than I expected, but the reason for that is that we just have so many Android-specific checks for XML resources and build files and like Gradle and so on. All right, the built-in the built-in checks are only the beginning. Lint is extensible, and so you can directly depend on Maven libraries that provide extra Lint checks. So I've listed some on this slide. And in Android, we have a special library dependency format, the so-called AAR files, where a library delivering functionality can also include Lint checks in their payload. So in Android X and Jetpack Compose, for example, they ship with a ton of extra rules, and when you depend on the library, we also run the associated Lint checks. Inside of Google, we have a bunch of checks, also inching up towards 500. And of course, writing your own Lint check is why we're gathered here today. There are a bunch of other features too, and I don't have time to cover them, since the point here is to learn how to write your own checks. But I'll just briefly highlight the last one. Lint tries really hard to be performant. It's a very, very relative term, but a lot of engineering work has gone into it, and it's going to show up in some of the API choices that we'll see a little bit later. All right, so that's enough preamble. To help motivate the technical discussion, let's take a first look at a simple lint check. So I'm going to gloss over some of the details so that you get a high-level picture of what the different pieces are. So let's assume that we want to warn people not to use Java util date, at least the one where you're not passing anything to constructors. So it's constructing the current time. In that case, you should probably use java.time APIs. So that's going to be our lint check. IntelliJ already has this inspection, right? So this is just an example that is easy to understand. All right, so the first step is to describe static metadata about the issue. So this information is constant, and in the tool integrations, this information is used to, for example, sort the entries or to explain the problem in more depth if the user asks for it in the IDE, and so on. So the first thing we do is we give it a unique issue ID. Here I've picked old date. And then the explanation lets you describe what the problem is and how to fix it, ideally in more detail than I've done here. You can decide a category for the issue and whether it's an error or a warning. And last but not least, we point to the implementation that is going to actually find or detect these issues, and I've called it a void date detector. So you register one issue type for each type of problem that you want to report, and you aggregate all of those issues into an issue registry. Lint is going to find your issues via the service loader mechanism in the JDK. And so here you get to put information that is common to all of your lint checks. For example, who you are, where to file bugs, and so on. So when lint runs in the output for third-party checks, it's going to include that information, makes it easier for your users to find you and report false positives, for example. So that's the metadata about the problem: ID, description, explanation, severity, and so on. So now on to the code, which is actually going to find and report these type of problems. That's called a detector. And so here's our detector. It's very, very simple. Lint has a number of callback methods where you register an interest in something, and then there's a callback when that thing is found. So here in the first override, I'm telling Lint, we're interested in anyone constructing the class Java util date. And so when Lint finds that, it invokes the second method that we've overridden, visit constructor. And so here we're passing the constructor call. It's the second parameter, the node argument, that corresponds to the constructor call. So here we just make sure that there aren't any arguments passed to that call. So, just parentheses. And all we do then is report the usage. We have an error message that we've crafted, and we also pass in a location that we can derive from the call location. And that's it. So when we run this in the IDE, we see this. We get a yellow highlight because we declared this to be a warning. If it was an error, you get a red underline. In the light theme, I actually usually use the dark theme. And if we hover, we get the error message that came from the report call. Notice also that there's a more link. So if we press that or the keyboard shortcut, the dialog updates to include more text. And this is the explanation message and some of the metadata that we registered in the issue registry. Notice also how the code fragments like java.time are shown with a code font. That's because we wrote our error messages and the metadata using Markdown. So I've highlighted that here. We have backticks in both the explanation and the error messages, and that means the text should be formatted as code. And this doesn't just show up in the IDE, it also shows up in, for example, HTML reports from Gradle. So here's a screenshot from an HTML report. With this warning, we can see inline code rendering here as well. All right, so we've got the detector working. So let's write a test. Lint is ideal for test-driven development. So I often start with a unit test, especially when I'm fixing a bug like a false positive or a false negative. And the fastest way to debug is just to have the target scenario as a test and then keep running it and tweaking it until the test passes. So here's a basic Lint test. Lint has a fluent test API, so we construct a testing task Then we configure it with a set of test files, and these are described inline as raw strings. Thanks to IntelliJ's nice nested language support, they get proper syntax and semantic highlighting in the IDE when you look at the tests. Then we indicate which issues to apply for this test, and then we run it, and then we check the result. So what I do here is I start with an empty string. This is wrong. We're not expecting empty output here. But then I run the test and see what happens. And of course, it fails. So what I do then is click on the show diff link in the output, or Command D. And then we get this diff output. And you can see that on the right hand is the actual output now from Lint's test. And so it looks like the Lint test is working properly. This is the text output we would get if we were to run this check in Gradle. So then I just copy that text, and I paste it into the expect string in my unit test. So now we have a passing test. It's checking that for this test source, we get exactly the expected output. And this part of the testing support is very deliberate. Notice how we're highlighting exactly with an underline where the expected error is. That's the range that's going to be highlighted in the IDE. It's kind of obvious what should happen here, but there are other testing frameworks for other static analysis tools which just say things like, there should be 3 errors, or there should be an error on the next line. But then it turns out they might be selecting the whole line, including the long argument list, or including the long receiver, and so on, which is pretty noisy in the IDE. So we want to be very specific about the error ranges. All right, so far, we've just tested that the lint check works with Kotlin. But we want to make sure that we warn anyone using Java util date, not just from Kotlin, but also from Java. So let's see what will happen when we add a Java source file. We add another descriptor to our test. So I'm going to run it, and of course it failed. So I got the new message, and what you can see here is it's now listing both the Kotlin violation and the Java violation. And we didn't update our detector at all. It worked for both. And that's because of the abstract syntax tree, UAST, which we're going to talk about shortly. But let's round out the example. So back in the IDE, if you press Alt-Enter when the caret is on the warning, it automatically shows a quick fix to suppress the problem. Remember how we defined the issue ID? Well, it shows up here in suppress annotations or comments. It can also show up in your build files if you want to suppress this issue, for example. So choose your issue ID carefully. You can't change it later. All right, so we can add our own quick fix too. We just pass a fix descriptor when we report the issue. So this is another Fluent API. We create a fix descriptor, and so for this, we want a string replacement. We're going to replace date with the localtime.now method. And notice how we're using fully qualified names here. We don't want to risk that there's already some other local time imported in the class. And we don't want a missing import error after applying the fix either. So we also tell Lint to shorten the names if possible. So that means that if there are no conflicts for the short time in the same compilation unit, then it's going to add an import for us and shorten the replacement string. So when we run this in IDE, we now get a fix proposed when we Alt-Enter. And notice that IntelliJ shows previews for quick fixes in recent versions. I love that feature. And so our quick fix shows up here. And you can see that in this case, it's going to both import the class and replace the constructor call with localtime.now. And of course, we want to have a test for this too. So on the test DSL, on the checked result, we can also check the fixes. So the way this works is that we just specify that we want to see the expected diffs from applying all the fixes to this same unit test. So similar to what we saw in the IntelliJ preview earlier. So again, I just start with an empty string, and then I run the test, and it fails. And of course, here we get to see the diff output, which I then copy into my test. And so here's our unit test, which now also checks that the quick fix is working correctly. I remove the Java test file here, but it's the same output plus a semicolon. And perhaps they don't want to offer switching to local time. Maybe the date usage was meant to include the date as well, not just the time. So we can offer multiple fixes. So we construct all the alternatives here and wrap them with a single quick fix which nests all the alternatives. And when we run that, we get all the fixes presented in the IDE for the user to choose from. And again, when we run the unit tests, Lint will iterate through all the incidents, and for each incident, all the fixes, produce the diffs, and give me that as a unit test. All right, so that's a high-level picture. You describe the issue type you want to identify, and then you write the detector to identify it. Sometimes you offer a quick fix, and you definitely write a regression test to cover it all. So I glossed over the detection part. I picked a very simple example, but that's usually where all the hard work is. So let's dig into that. So I talked about how lint analyzes all kinds of languages. You can use DOM for XML, you can use ASM for bytecode, and so on. But this is Kotlin Conf, and we don't have a lot of time. So let's just narrow our focus to analyzing Kotlin and Java code. And so you may wonder, why bother with Java at all? So let's say we wanted to write a lint check which prevents you from using the not null assertion, the double exclamation mark operator in Kotlin, also known as bang bang. That only applies to Kotlin. So we could write a Kotlin-specific check directly using Kotlin compiler internals. But in my experience, that's not a common scenario. Most checks in lint aren't language-specific. They're API-specific or they're bug pattern-specific. For example, incorrectly using the wrong formatting character, or calling it dated API, pun intended, or forgetting to look at the return value, and so on. So it's really important to have this lint check work not just for new Kotlin code, but for older legacy Java code in the code base as well. And you don't want to have to write the check twice, once for Kotlin and once for Java. So the heart of static analysis is the abstract syntax tree, or ASTs. So here you can see the AST for a very simple Java program shown at the top, the way it's going to be represented in IntelliJ today. So this is actually a simplified view. In reality, there's also whitespace nodes tracking all the spans of whitespace between these nodes. So anyway, you can see there's quite a bit of detail here, tracking things like keywords, variables, references to, for example, the package, and higher level concepts like a class and a field, which I've marked with a thicker border. And here's the corresponding Kotlin AST, again in IntelliJ. This is for a program that is completely equivalent to the Java one. But notice that this is a completely different shape. So here they are side by side, or yeah, you get it. So they're totally different. They reference different element classes. You have PSI class versus KT class, and on all the way down. But there is some commonality. They each have a node for the file, for the class, for the field, for the initial value, the string. So we can construct an AST which represents the same concepts. So here it is. This is a unified AST in something called UAST, which is short for Universal AST. So UAST is the primary AST representation for code in lint. All the node classes here are prefixed with a capital U for UAST. And so what you're seeing here is the AST for the Java class shown on the left, and here's the UAST for the equivalent Kotlin code. This looks almost the same. So if we see them side by side, they're not always identical. For strings in Kotlin, we often end up with an extra parent UI injection host, but for our purposes, you can see that the ASTs are mostly the same. And if you handle the right-hand side one, you'll handle the left side one as well. And so that's why our Java util date check just worked for both out of the box. So UAST is the preferred AST when you're writing lint checks for Kotlin and Java. It lets you reason about things that are the same across languages: declarations, functions, superclasses, assignments, if expressions, return expressions, and so on. And when I started out, I had a fundamental misunderstanding about UAST based on the name. I thought universal part meant that it was a superset, that it's an AST that can represent everything needed by all languages. But that is not the case. Instead, a better way to think of it is as the Java view of the AST. So if you look at the very simple class on top, it's a Kotlin class, it's a Kotlin data class, which has two properties. So you might expect that UAST would represent this as a U data class with two U property children, right? But Java doesn't support properties. So if you try to access this data class from Java code, which you can see that I'm doing in the code completion pop-up here, you can see that we're just being offered the generated getters and setter methods from UAST, and the methods generated from the data class, the copying constructor and the component methods for destructuring. So these methods are directly callable from Java, so it makes sense for UAST to expose them so we can reason about them. So here we have a very simple Kotlin file for a single Kotlin property. But notice at the UAST level, there's no such thing as top-level methods or properties. In Java, everything is a class, so Kotlin C will create one. It's going to be the file name plus KT. So we see our test KT class, and there are 3 members here. That's the getter and the setter for this property, and the private field itself, which is where the property is stored. So this all shows up in UAST. It's the Java view of the Kotlin code. And so this is going to maybe seem limiting at first, but it's actually what you want. It makes it really easy to learn and reason about APIs and so on. So you may have gotten the impression that the UAST tree is very shallow and only represents high-level concepts. That is not the case. It does skip things like white space nodes and individual keyword nodes, but for something like the expression we see on the left, you can see that everything is modeled. And here I'm only showing the return value itself, if expression, binary expression for the comparison, and so on. Now, every node in UAST is a subclass of UElement. So there's a parent pointer, which is handy for navigating around in the AST, and there's also a source PSI property. So this lets you map from the abstract UAST code down to the specific PSI elements we saw earlier. So here's an illustration of that. So we have our UAST tree in the top right corner, and there's the Java PSI behind the scenes. So we can always access the underlying PSI node for a U element by accessing the source PSI element. So when you need to dip into do something language specific, especially for Kotlin, that's very trivial to do. And in some cases, these references are null. Each of the UElement nodes point back into the PSI AST, whether it's a Java AST or Kotlin AST. So here I'm showing the type of source PSI for each node in our earlier simple UAST tree. You can see that the class generated to represent the top-level functions does not have a source PSI, because in the Kotlin PSI, there is no real class. Right. So the real skill you need for writing these lint checks is understanding the AST and then doing pattern matching on it. And a simple trick for this is to create the Kotlin or Java code that you want, for example, in a unit test, and then in your detector, you recursively print out the UAST as a tree. Or in the debugger, anytime you have a UElement, you can call as recursive log string on it, and you can see what you find. So going back to our original example lint check, here's what the UAST dump looks like for that test file. So we can see types of nodes in the AST, UFile, UImport statement, UClass, UMethod, UBlock expression, and on and on. But the pretty printing of the UAST isn't super descriptive. You see the node types, and sometimes you want to help orient yourself where you're looking in the source code. If you're, for example, looking at a block expression, well, which block expression is this? Here's a simple trick. For that, I just used the source PSI.text property. This is going to show you the source fragment corresponding to the node. And I sometimes do the parent's source pointer instead. The stop ship line comment suffix triggers a lint check, which makes sure that I don't actually check these in. That has happened before. All right, so now that we've seen ASTs, our original lint check could have been implemented as on this slide. Here we visit the whole file, and for each call node, we see, is it a constructor? And if so, is it constructing a date? And if yes, then we report it. But this would be incredibly inefficient. If lint checks all visited the file on their own, for a single file open in the editor, every time you stop typing, we'd potentially visit the entire AST repeatedly over 1,000 times as each lint check took its turn. So instead, lint tries to only visit the AST once. So here's our original detector again. We're not using our own visitor, we're just implementing some callbacks to lint. So in the first method override, we're telling lint upfront which classes we're interested in. Lint collects all this information from all the lint detectors upfront once. Then it creates a bunch of jump tables, and then it does a single visit over the AST. So when it comes to a constructor call, It looks up which class is being constructed, and then it looks up which detectors care about these classes, and then it just delegates to them. And this makes things a lot faster than our custom visitor, which visits the whole file for each detector. All right. By the way, one of the superpowers of UAST is the ability to resolve. So for a call, figure out which method, possibly overloaded, is being called. So in our slow implementation, we took each constructor call and resolved it to see which constructor is called and then which class is inside. So resolving works for a number of element types in the UAST, methods, references, and more. And so this is a major advantage of using UAST even for Kotlin code, because resolving is a lot easier than with PSI. One thing to note, though, is that when you resolve, you don't point to a U element, you point into PSI. And that makes sense because you can call stuff that's in jar files, and there's no code there to reason about. But if you do resolve into code, we'll see later that it's very easy then to get back to UAST with the to-U element function. All right, so it turns out there are some very common patterns that most lint checks fall into. So we made those extra easy to write and also efficient for us to perform. So we've already seen the constructor call callback that we use for our avoid date detector, but by far the most common one is method calls. Tell me when someone calls a method named lazy, for example. So this is a simple check which warns about using the by lazy construct. This is actually a Kotlin-specific check, and it's not one of the built-ins, by the way. Just an example, but note that even Kotlin-specific checks are easier to write in UAST because they benefit from the shared visitor paradigm as well. So what we do here is check the call, for example, to make sure that it's in the right containing class, and maybe that it has the right signature. And so here I've emitted the code where we look to see if it's passing in a threading mode, which we want to allow. And if it matches, well, then we report. Sometimes, sometimes this is just a starting point. So here, for example, is a lint check making sure we always call close on a file reader or an input stream and so on. So we first use the method or constructor callback to narrow our analysis to just constructions of input streams and file readers. And then in the body of that callback, well, now we construct a control flow so we can make sure that all paths lead to a close call. You can also check if a particular name is referenced. This is similar to the method call support we just saw, but meant for fields. And another one is, let me know when someone creates a subclass, or whether anonymous or not, of a given class or interface. So in our Android Studio code base, for example, we have this check that I'm showing here, making sure you don't subclass a swing worker class from the JDK, but IntelliJ's own special purpose one. This one is a bit more general purpose. You get to look at one or more specific element types. So here, for example, we want to look at all the strings in the file and check whether they have a certain prefix. So this is the closest you get to writing a custom visitor typically. But this is going to only be invoked for the specific string literal nodes, not the whole tree. Here's my personal favorite, the annotation support. So here, for example, is part of a built-in lint check for the @discouraged annotation in Android X. So some APIs can be annotated with @discouraged and an optional custom message. And the annotation support handles all kinds of scenarios. So we have this annotation usage override. So we can let the detector check all kinds of annotation usage scenarios. Here are some possibilities. Maybe you care about an annotated element being returned, or maybe used in an inequality check, and so on. Another wrinkle to think about is that in Kotlin, you have features like operator overloading. So here we see two equivalent calls, P1 plus P2 and P1 dot plus P2. These are both going to compile down to exactly the same thing. But now let's take a look at the ASTs. So the left half of the graph, or the tree, shows the first expression, P1 dot plus P2. And the right half shows the nice operator function corresponding to the plus sign operator. Notice how these have different shapes, different types in the tree. One is showing up as a function call, and one is showing up as a binary expression. So this is deliberate. If UAST were to paper over this, it might make it very difficult to write a lint check encouraging you to switch from a function call to the operator syntax, for example. But it does cause some headaches for lint authors. If you visit the AST yourself, you have to be aware of this. If you only visit call nodes, you're going to miss the operator overloads. And this also applies, for example, to array access. So for the code fragment shown in the bottom left corner, Kotlin lets you access a setter method using array assignment. So for the nice array syntax, we have an assignment node in the tree on the left half, and our special call is on the right. And so this used to be broken in lint. We'd get a bunch of false positive or false negative bugs that we weren't handling operator overloads. And so what we're doing now is we construct these, we handle it for you basically. We create these wrapper calls and pass those to you instead. And in your own visitors, if you run into this scenario, you can also call our .asCall method on a U element for one of the node types that need it, like binary expressions, array expressions, prefix expressions, and postfix expressions. So for the binary operator, for example, you now get a call with the parameter list, which has the right-hand side of the operator as the first and only argument, and the left-hand side is the receiver. All right, so sometimes you do need to dip into language-specific Kotlin or Java PSIs. So let's say you want to know if the current class is a companion object. You could cheat and look at the class name to see if it's a companion. But that's not quite right. In Kotlin, you can specify a custom companion object name, as I'm doing here. And of course, your users are free to create classes named companion that aren't companion objects. So the right way to do something like that is to look up the source PSI attribute. In the debugger, you can see what the concrete PSI element is and use code completion to explore it. And as you can see, it's actually very easy to see if the PSI element is a companion object. So using Kotlin PSI was the state of the art for correctly analyzing Kotlin code until recently. But when you look at the PSI, you'll discover that some things are really hard, in particular resolving and especially dealing with types. Lint doesn't actually give you access to everything you need in Kotlin if you want to look up types. You need something called a binding context, which was not provided to you. And that was deliberate because that was an implementation artifact of the old compiler. And you probably heard here at KotlinConf that there's this new compiler called K2. And this is a complete rewrite of the compiler front end. And as part of the tooling support for K2, there's a new API called the Kotlin Analysis API that you can use to dig into details about Kotlin. And again, for most lint checks, you should use UAST if you can. But when you need to know some really detailed Kotlin stuff, especially around types, smart casts, null inference, and so on, don't hack. Use the Kotlin Analysis API. It's your best friend. So here's a simple example. So here we have a scenario where we know that the to-do will never return. So Lint can take advantage of that when analyzing the control flow. And in particular, it should understand that after the to-do call, there's no chance of fall through. So it can conclude that SDK int must be at least 11. So the way the Kotlin compiler can reason about this is that the to-do method in the standard library has a return type of nothing. And here's Lint's old way to handle this scenario. It just had a hard-coded list of these nothing returning methods, error and to-do. It would also look up the containing class to make sure that those are the methods from the Kotlin standard library. I've skipped that here. But this is super hacky. And more importantly, it doesn't work for library code or your own code using the nothing return type. But recently, the Kotlin Analysis API made it not just possible, but easy to handle this. So here's the new implementation. The entry point to all Kotlin Analysis API usage is to call analyze and to pass in a Kotlin PSI element. So this creates a session, and it's very, very important that you don't hold on to any objects inside a session and reference it outside. If you do need to hold on to something, create a simple pointer. So anyway, there's a huge number of extension methods that take an analysis session as a receiver. So inside this Lambda, you get access to a bunch of new methods that helps you with the Kotlin Analysis API. So on a KT declaration, I can call getSymbol. On a KT expression, I can call getType. And so KT symbol and KT type are the basic primitives we're working with in the Kotlin Analysis API. So here, for example, we resolve the call, look up the corresponding function, which of course is a KT symbol itself, and from that we get the return type, and then we can just check if it's a nothing type. And this API works with both the old compiler and K2, which you can turn on in lint already with the flag, and it's going to be the default very soon. So I recently had a this pointer in the middle of some detailed Kotlin PSI analysis, and I needed to resolve it. What is this pointing to? But I wasn't sure how to do that. And then I realized that UAST can do it. So I wrote this expression in my editor, and then I stepped into the try resolve call. So what's happening here is that you can always call to element on a PSI element, and UAST will try to wrap it with a U element. And now we can use UAST's nice resolve support. So I stepped into the function, and this took me into UAST. And because I'd turned on K2, the whole implementation of UAST there was using the analysis API. And so from looking at what that code in UAST was doing, it was trivial for me to extract the basics of it. And as you can see, it was actually very easy to do this. Another big advantage of the Kotlin Analysis API is that it gives you access to reason about compiled Kotlin code in the same way that the compiler does. So normally, when you resolve with UAST, you get a plain PSI method back. You can see that here from the debugger. We resolve the error method in the Kotlin standard library, but it's just a PSI method. It's not a KT element. So it doesn't have all the Kotlin payload, special modifiers, whether it's inline or infix, default parameter values, and all that. So you can see here that its return type is void, and we know that should be nothing, right? So the analysis API handled this properly, even for compiled code. In fact, we've already seen this work because the error and to-do methods that we handled earlier are, of course, coming from the compiled Kotlin standard library jar. So I already showed you that the right way to check if something is a companion object was to use Kotlin PSI, but that's only true if you're looking at source code. If you've resolved the class, well, now it's not going to do the right thing. You have to use the Kotlin Analysis API. All right, so now I'm going to rapid fire mention some additional facilities to be aware of that can make your lint checks a lot more powerful. So first, there's the data flow analyzer. It's used for a bunch of lint checks. If you want to make sure that after calling one method, you also call another on that same instance. So for example, if you create a database transaction that you call commit on it. So lint keeps track of the transaction instance and follows all the flow through the method in case the reference gets copied into other variables and so on. And as a user of the data flow analyzer, you just tell it to start tracking instances on a particular call, and then you have a callback where you can decide if the target has been reached. And it's very easy to see if the value escapes by being stored in the field or passed to another method and so on. Lint's test DSL is also very rich. And my favorite part about it is something called test modes. So you can add some of these yourself, but we have a bunch of built-in ones. So here's how that works. So let's say you have a simple lint check like this. All we're doing here is complaining if in a binary operator, like plus, the left-hand side is a function call named sum. Yeah, it's dumb, but it's just an example. So we run our test the first time and update the expected error message such that the test is passing. But when I run the test, it still doesn't pass after this. So here's what I see in the IDE. So what's happened here is that lint reran the exact same test scenario, but this time it went and inserted parentheses everywhere that is legal in Kotlin to put them, except for some very unlikely combinations probably no one will use. And then in the test output, we can see the modified test source with those extra parentheses. And so this makes your lint checks a lot more resilient. We ensure that you consider not just the specific test you wrote, but a number of variations of it. So fixing this is easy. Parentheses actually appear in the AST. So when looking at an operand, we have to skip through the parenthesis node. And so there's a built-in method in UAST for that. So when we add that additional method call, well, now the test passes. So there are a bunch of similar scenarios to this that Lint includes by default. So all of them tweak your tests in some way and expect the test expectations to remain the same. So it'll catch if you, for example, handle if blocks but not when blocks in Kotlin, or if you have braces or not, inside your if statements, and so on. So just as a fun aside, I heard in the Kotlin Conf keynote a couple days ago that a future version of the language is going to make it easier to put $ in raw strings. Yay! Using a syntax like this. You put a couple of $ in front of the raw string declaration. So now you're allowed to have a single $ without substitution. Well, Lint has had to deal with this for a while in our unit tests. As you can imagine, $ appear in a lot of places, for example, in Kotlin source files with string substitutions. All right, so what we do is this. When we output results under the test DSL, we just replace the $ with the $ lookalike. It's a different Unicode character. And so Kotlin C will ignore this. And so the output looks reasonable, but it's not actually a $. And so you can copy that text as your actual expected string. And of course, when you run again, the reason it works is that we do the reverse mapping as well. Like, we look for that special lookalike and we make sure that it's a $, again, before Lint really runs. So then we get this nice result. This is a test descriptor for a Gradle KTS file, for example, where we have a variable substitution. So I bolded the fake variable substitution sign here. So it's worked pretty well in practice, but I'm glad there's a better way coming. I'm not proposing this as another keep for Kotlin. All right, so here are some more topics for further exploration. I don't have time to cover these today. I didn't know what I was thinking when I thought I could cover Lint in 45 minutes. So I'll just leave these to encourage further study. So you can write more powerful quick fixes than what I've shown here. You can add options to your Lint checks, for example, booleans or integers or even files, in case you want to make your checks more configurable by users. Partial analysis is an important and big topic for scalability. And normally, your detector looks at the source code once, but there are ways to request doing multi-pass analysis. As mentioned earlier, you can easily analyze other types of files as well. And we talked briefly about the data flow analyzer, and there are many other helpers as well to make it easier to write more powerful Lint checks. Does class A extend class B, for example? And there's special support to let you change your error messages in your check without invalidating baseline files. Before I go, I want to mention that we actually have quite a bit of documentation for Lint. So here's a screenshot of a few pages from Lint's API guide. It goes into a bunch of details, 13 chapters, 133 pages, with code snippets, illustrations, and so on. So if you get interested in writing a Lint check after this talk, do check out that resource. It doesn't have anything on the Kotlin Analysis API, though, but I might spend the flight home adapting this material and expand that into the API guide. All right, thank you so much. I'd love to connect with you on Threads, and please don't forget to vote, because I'd love to be invited back. Thank you.